Good morning, everyone. Today I'm going to present to you two topics, the liquid state and the solid state of pharmaceutical substances employing the principles of physical pharmacy. Okay, first, I would be presenting the liquid state. Okay, when a gas is cooled, it loses some of its kinetic energy in the form of heat, and the velocity of the molecules decreases. If pressure is applied to the gas, the molecules are brought within the sphere of the van der Waals force or van der Waals interaction forces and pass into the liquid state. Because of these forces, liquids are considerably denser than gases and occupy a definite volume. The transitions from a gas to a liquid and from a liquid to a solid depend not only on the temperature but also on the pressure to which the substance is subjected. So that is what we have learned from our last discussion when we had a discussion on gases, right? And the transition from gas to liquid. We all know that the two variables that are needed in order to liquefy a gas are temperature and pressure. That is, by decreasing the temperature and increasing the pressure, we will be able to um, change, okay, or convert a gas into liquid, and vice versa if we're going to do alteration of those variables. However, when temperature is continuously increased, so that is during the time when heat is continuously applied to a certain matter, okay, a certain amount of pressure applied will not make it possible to convert the gas into liquid form. So in our attempt to convert a certain gas into a liquid, diba, all we have to do is to modify the temperature, uh, decrease the temperature and then increase the pressure. However, if continuous heat is being applied, continuous kinetic energy is acquired by the gas molecules, there will come a time that even though certain even though a certain amount of pressure is applied, it can no longer make it will no longer be possible to convert that gas into liquid. Okay, so in that particular instance, the temperature is already in its critical state, or the temperature that occurring in that phenomenon or in that condition is what we call as critical temperature. Now, what will make the conversion possible is the application of another critical value. We call it critical pressure, which is the pressure required to liquefy a gas at its critical temperature. So it is also the highest vapor pressure that the liquid can have, or a liquid can have. Now, critical temperature serves as a rough measure of the attractive forces between molecules because at temperatures above the critical value, the molecules possess sufficient kinetic energy so that no amount of pressure can bring them within the range of attractive forces that cause the atoms or molecules to stick together. So it only means that if you have a high critical temperature, it will require higher critical pressure. Therefore, it only means or show that there is a uh, lower force of attraction that is existing already. So if there is a low force of attraction that exists between gas molecules, it will be difficult for the gas molecules to be made to come in closer contact with each other. So mahirap magpa-liquefy ng gas. Now, gases can be liquefied through the following. So, use of freezing mixture. So, you have there examples of commonly used freezing mixtures in pharmacy preparation. So, you have the common salt, okay, which common salt and ice, which is able to or which can cause a negative 20 degrees in temperature. Calcium chloride and ice, which can cause a negative 54 degrees in temperature, and combination of solid carbon dioxide and ether, which can bring about a negative 110 degrees centigrade temperature decrease. Okay, 110 degrees centigrade temperature decrease. Now, gases can also be liquefied through forced cooling, which in a way exhausts the gas to reduce its kinetic energy. Okay, and then it might lead to the conversion of phase from gas to liquid. Now, this process may be done through what we call as adiabatic expansion or application of the Joule-Thomson effect. Okay, so which is actually focused on decreasing the temperature. Now, I have here uh, a short clip showing adiabatic expansion. Okay. Now, adiabatic expansion is achieved by carrying out the process in a dewar or vacuum flask, which effectively insulates the contents of the flask from the external environment. The work done to bring about expansion, therefore, must come from the gas itself at the expense of its own heat energy content. So that would be the collision frequency. As a result, the temperature of the gas falls, okay, because the gas are actually exerting energy. If this procedure is repeated a sufficient number of times, the total drop in temperature may be sufficient to cause liquefaction of the gas. So as you can see in that animation, you have the gases placed in a certain vacuum. Okay, the piston here, the piston here represents pressure. So, for example, if without the pressure applied, you can just see the gas molecules freely floating around. So, if pressure is applied, so there's a tendency of the gas molecules to become agitated. Okay, and then frequently cause collision among themselves and in the sides of the container. Okay, now in an adiabatic expansion, there is no heat being supplied. Okay, there's no heat being supplied into the uh, into the contents of the vacuum flask. Okay, so there's no energy, there's no kinetic energy that are acquired by the molecules within or inside, and thus there's no the gas molecules eventually after such time will be exhausted, and then that will bring about the what uh, liquefaction because there's no uh, kinetic energy, okay, that may be used by the gas molecules to what to move freely around. Okay, now another way of liquefying gases is through the Joule-Thomson effect. Now, a cooling effect is also observed when a highly compressed non-ideal gas expands into a region of low pressure. In this case, the drop in temperature results from the energy expended, okay, or spent in overcoming the cohesive forces of attraction between the molecules. Okay, wait, sorry. Let me just finish my ano. Okay. Uh, this cooling effect is known as the Joule-Thomson effect, and it differs from the cooling produced in adiabatic expansion, in which the gas does external work. So to further understand, I have again here another clip. Okay, so before we proceed to discussing another property of liquids, uh, I hope that you have understood what the Joule-Thomson effect is about. Okay, so in contrast with the adiabatic expansion, I hope you are able to differentiate that adiabatic expansion is the process of liquefying gases at the expense of the own energy of the gas molecules, okay, that are being exerted. Okay, and then there is another thing that you have to remember for the adiabatic expansion. The process is being conducted in a vacuum flask. Okay, so what we have in the laboratory is a Dewar flask named after its inventor. So that is a vacuum flask wherein heat, okay, energy can neither come in or get out from within, siyempre, the system. And then for the Joule-Thomson effect, so that would be, the emphasis would be uh, that the liquefaction is brought about by the exertion of energy of the gas molecules as they move from a region of high concentration to a region of lower concentration. It's just like when you are traveling, for example, uh, when you are moving from a region of definitely yun lang sa ano sa pag-move mo from one place into another, so you spend energy in doing so. So initially you have this high energy before starting or initializing the work, and then after some time that you have covered let's say long range or long distance na. Okay, so eventually you will become tired, and then that's basically the same thing that happens to the gas molecule. So after exerting the kinetic energy, eventually they become exhausted, and that exhaustion leads to the transformation of that gas molecules to liquid. Now we have here another property of liquid, so vapor pressure, which is also related, okay, to the transformation, or which is also tama related to the or occurs or that is observable rather during transformation of your gases to liquids. Okay, so let's view the clip. Okay, there you have it, the two presentations discussing vapor pressure and boiling point, which are two properties of your liquid substances. Okay, now we have here, okay, shown in the slide, Clausius-Clapeyron equation, which is a very important and very helpful equation in trying to understand the heat of vaporization. Okay, so you have there the formula. All you have to do when when you encounter problems involving um, involving heat of vaporization, all you have to do is to substitute the values the nandun dun sa formula. So that's the beauty of computation sa physical pharmacy. So the values are there. All you have to do is to substitute. And there are times that you would have to derive a a certain formula from the original formula, but I know that you can manage with that because that is basic algebra lang, di ba? Anyways, so the Clausius-Clapeyron equation expresses the relationship between the vapor pressure and the absolute temperature of a liquid, the two factors that we uh, every now and then frequently mention that are involved in transformation of gas to liquid, liquid to gas. So you have there the formula, the variables, P1 and P2, the vapor pressures and absolute temperatures T1 and T2. So if you may recall the STP, the standard temperature and pressure. So the standard temperature is measured or expressed in degree Kelvin, and the standard pressure is either expressed in atmosphere or millimeter mercury. Now, H sub V is the molar heat of vaporization, and that is defined as the heat absorbed by 1 mole of liquid when it passes into the vapor state. So that is what we usually and frequently compute for. Okay, so how much heat is absorbed when 1 mole of liquid passes into the vapor state. Now I have here, this is lifted from the Martin's Physical Pharmacy book. I know that you also have access to this e-library ng perpetual, diba? So this is how, this is what I mentioned. All you have to do is to substitute the formula, the values given. That's a problem, and then you can compute now for the needed or the unknown. Uh, so yeah, so I'll just leave that with you so you can practice, and then later, maybe sometime during the assessments, in future assessments, I will be giving you related exercises sa computation ng heat of vaporization. But all I have to do is to remember the formula. Whenever I give exams, I give the formula. So your memorization of the formula will now be based on familiarization na. Pero it will help pa rin, syempre, if you are going to jot down yung mga formula ninyo para mas madali nyo silang matandaan. Okay, so in the previous two videos, it was mentioned na boiling point, right? So boiling point is considered the temperature at which thermal agitation can overcome the attractive forces between the molecules of a liquid. So boiling point provides a rough indication of the magnitude of the attractive forces. So sabi nga din natin, di ba, the higher the boiling point, it means there is a stronger force that exists between the molecules. That's why mahirap silang mapahiwalay. So the higher the boiling point, the stronger the attraction between the molecules. The lower the boiling point, the lower the boiling point, sabihin, it will only take minimal amount of force to break the intermolecular attraction that exists between the molecules. And also pala, so what you have heard in the video kanina, that different substances have specific boiling points or at least boiling point ranges. So it will also help in identifying the substances as well as determining its purity. Okay, so if you have a mixture of solutions, if you have a mixture of solutions, definitely hindi ka naman makaka-hit ng boiling point value within what is listed here if it's a mixture. But if you have a pure substance, let's say for example pure water, you will have boiling point at 100 degrees. If it's pure ethyl alcohol, then you have to expect that the boiling point is around 78.3 degrees centigrade, or plus minus 1 or 2 yan. Okay, now so that would be the end of the lecture for the liquid state. So at this point, you will be given, or you are given, a short quiz just for a review and assessment. So you can now access the quiz and then yun, take the quiz, or you can take it later after we have review. So no pressure, no pressure. I don't want you to liquefy. So you can take it at a later time. So after this, say I will be presenting another set of lecture that would be the solid state. Okay.